Introduction to Electrochemistry. This is part 1 of our electrochemistry lectures. Alright, so let's think about electrochemistry. And basically, this is the interchange or the conversion of chemical energy into electrical energy. The first battery was constructed actually quite a while ago by Alessandro Volta in 1793. Now, electrochemistry is really important in that it provides a way to use the free energy in chemical reactions, so energy that is available in spontaneous chemical reactions is used to do electrical work. And we can represent this work in terms of charge and cell potential. So Q is the charge transferred and delta E is the potential difference between the two cells, and we'll see more about that in just a second. Now, I want you to recall from chapter 4, oxidation and reduction. So these reactions involve the transfer of electrons from one element in the reaction to another. And they always go together. So something's always going to be oxidized and something's always going to be reduced. So one element oxidized. And when that happens, it means it loses electrons. So we'll see some examples of that soon. In the same reaction, another substance is reduced. And that means that it gains electrons. And it gets those electrons from the other element, which is why they always have to go together. So again, just to reiterate, make sure you remember this, that oxidation and reduction always happen together. So here's an example reaction. So we have copper solid, and it's going to react with 2 moles of silver ion, silver plus 1 ion. And these are in solution. And during that reaction, we're going to get copper ions, so the copper solid will be converted to copper 2+, and the silver ions are going to become silver metal. So we have to think about this. Which substance is reduced and which one's oxidized? We'll look at that on the next slide. And we also want to look at the oxidation and reduction half reactions in this process. So we're going to separate out the half reactions and look at them separately. So we have our overall reaction at the top of the slide. In this case, we can see that copper metal loses electrons, and so when it does that, so here they are, it's going to be oxidized to copper 2+ ions. And just as a preview, this generally happens in the anode compartment of the electrochemical cell. So we're going to see that in just a few minutes. Now, silver plus in this reaction, so we can see it right here, it's in solution, but when in the presence of copper metal, it will actually gain electrons, so 1 each mole of silver ion, and those electrons are going to come from our copper metal like we just discussed. So we're going to end up with copper 2+ ions, and we're going to end up with silver metal in the cathode compartment. Now, in this case, silver plus gains electrons, and so we say that it is reduced from +1 to 0. So it's reduced in charge. And you can see the half reactions here. So copper solid goes to copper ions plus 2 electrons. And for silver, in the reduction reaction, we start off with ions already oxidized in solution. We add 2 electrons, that's our reduction, and we're going to end up with silver metal. In an electrochemical cell, these 2 half reactions that we just looked at, they're separated from each other in space. And we're going to see a picture of that in just a second. Now, we do that so that we can harness that chemical energy for electrical work. And that's basically the use or function of an electrochemical cell. Here's a generalized voltaic or galvanic cell. You can call it either one. Both of them are correct. Now, we have an anode compartment and a cathode compartment. And oxidation is always going to happen at the anode in a voltaic cell or a galvanic cell. And so we're going to have an electrode, and that's going to be made of some metal, or as we'll see later on, it may be platinum, which is inert, with another reaction in solution that serves as an anode reaction. And in this compartment, we're going to have oxidation, and that means we're going to be losing electrons. So the anode compartment is always going to have the element with the lower standard reduction potential. We're going to see that later on too, and that's for, again, a galvanic cell. The cathode compartment. This is where reduction happens. We're going to be gaining electrons, and this is always going to be the element with the higher reduction potential. So we'll see that in just a few minutes. Now this salt bridge here, basically that completes the circuit, and so it prevents charge buildup in each half of the cells. If we didn't have the salt bridge, then electrons would flow from the anode compartment to the cathode compartment, and that charge would build up in the cathode compartment and the cell would stop. So just one last thing to just make sure we know, electrons are going to go from the anode to the cathode in a galvanic cell. Now, we get tired of drawing great big galvanic cells, the whole setup. It's very inconvenient and it's a lot of work. So cell notation was devised to simplify that. They're also called cell diagrams. And basically what you have here is an abbreviation. On the left side, you're going to have the anode half cell. And so the electrode is always going to be on the outermost position. And phases are going to be separated by a line or a bar. And then we're going to have the metal ions in solution. And all of that is the anode. So basically, also another way to think about this is the anode half reaction. This is the half reaction with the lower standard reduction potential. The cathode half cell also has the metal or the cathode on the outside. Okay, so always remember that the solid substance is going to be on the outside. And again, a line separates phases, and so in the cathode half cell, we're going to have the ions inside that, and these two double bars, they represent the salt bridge. So we just need a few more terms and conversions as we move through electrochemistry. So the potential difference is actually very important, and so you can see I have difference in parentheses, and so basically you'll see potential difference or you'll see just plain old potential, and it means the same thing. And this is the driving force for a galvanic cell. Now this potential is measured in volts, and so 1 volt is equal to 1 joule per coulomb, and coulomb is a unit for charge. So charge is measured in coulombs, and it's represented with a capital C. Now current, this is the amount of charge that passes a point in an electric circuit in a unit of time. And usually this unit of time is seconds. And so the definition for an amp or an ampere is 1 coulomb per second. A Faraday, this is the magnitude of electric charge in 1 mole of electrons, and it's given in coulombs as well. And so 1 Faraday, represented with capital F, is equal to 96,485 coulombs. We're finished with our introduction, so now we're going to look at a galvanic cell example. And this is the Danielle cell, and you'll see this in part 2.